Good day everyone. Thank you for the chance to present my article named Sensors and Simulations for Transport Resilience. My name is Maros Lacinak and I made this article in collaboration with my colleagues from the University of Žilina, namely Jozef Ristvej, Michaela Janosikova and Klco. Contents of the article and of this presentation include the introduction of the Laboratory of Simulation and Modeling of Crisis Phenomena in Transport, located at the University Science Park. Then we will cover our views on resilience, followed by the list of sensors that might be used for pregnancy of a number of resilience indicators. Let me now start with the first topic. The core of the laboratory is the simulation program VR Forces. This program enables the simulation of various types of crisis phenomena in real or fictional map background, thanks to 4 modules: mass traffic accident, dissemination and detection of chemical agents, chemical fields that can display consequences of the use of chemical weapons, contamination and also process of decontamination, and the leakage of radioactive substances. In the picture we can see example of created scenario on a map background of Slovak city, Trnava. There we simulate a traffic accident followed by a leakage of dangerous substances. The usage of this program is oriented mainly towards the transport system, where it is possible to create simulations of mass traffic accidents or accidents that involve the leakage of hazardous chemical agents, including radioactive substances. For our ambition to use this program in our resilience research, we aim to widen its use to enable collection and visualization of transport data from around the city. In collecting said transport data, we should focus on those that will allow us to acquire values of resilience indicators. Next topic, because the presentation of the program is not the main aim of the paper, is to set up the background for our research of resilience. For this purpose, we studied literature and opinions on resilience. We agreed with some, felt skeptical about others, and we concluded that resilient city design should result in city systems that are prepared to adapt to external changes in such a way that causes minimal changes in system operation and functionality. It should be among today's goals to utilize the ability of modern technologies to ensure systems functionality through different mutually independent channels. This way, mainly the critical infrastructure should be backed up so that failure of some channels would not mean the failure of the whole system. Based on studied definitions, we collected a group of keywords for our own view. We believe that the resilience revolves around these keywords: absorption, adaptation, continual functionality and recovery. A fast one, if I may add. Definition built around these keywords presents resilience as an ability to absorb crisis phenomena of various kinds with non-existent or minimal restriction of the subject's functioning, allowing adaptation of subject's resources, skills and infrastructure to restore its compromised functionalities as fast as possible. Now moving to the transport system of the city, definition of transport resilience is the same in the core, but some tweaks are made to express the nature of transport system. Therefore, we described transport resilience as the ability of transport system to absorb crisis phenomena of various kinds with non-existent or minimal restriction of traffic speed, possibilities and safety, allowing adaptation of traffic routes and means, resources, skills and infrastructure to minimize the time needed for a restoration of suffered traffic restrictions and for a recovery of compromised features of transport system. As the aim of our research is to propose a methodological procedure to measure resilience, we listed in our research indicators that we believe cover the resilience in its complexity. In this article, we focused on finding ways how we can collect indicators specifically with the help of sensors and simulation. We divided the indicators to two groups. Group that can be obtained by sensors that can be embedded in the infrastructure, and those that can be obtained, and we also believe enhanced, by the use of simulation. Not only did we make a list, we also tried to specify how the sensors and simulation can deliver needed data that can be transferred to the values of individual indicators. In the first group, we have indicators summarized in the screen. Daily traveled distance of citizens, redundancy for personal vehicles, trucks and mass transport vehicles, clarity of the traffic net labeling, serviceability of the road, and carbon neutrality. Tools that can help us to obtain them are mobile phone signals, sensors able to count the traffic demand with programmed Raspberry Pi device or similar. We initially thought about simply counting the number of vehicles that can be done by simple laser sensor, but later we thought about multifunctional use of cameras, and we might consider using only cameras with program for video analysis aimed at identification of traffic labeling, structural flaws in traffic infrastructure, but also aimed for detection of vehicles that will cross an exit point at the traffic nodes. Also, emission meters can give us information about carbon neutrality of the location. Second group of indicators consists of promptness to act, preparedness, possible speed of recovery, and failure consequences. These indicators are tied to the management and crisis teams of the cities. Now I will finalize the circle, getting back to our laboratory introduced at the beginning, because for these teams, our laboratory prepared training aimed to improve these characteristics by solving a case that will be prepared as a simulation scenario, and the teams will be expected to react accordingly, cooperating with rescue units and dealing with the situation. This should help them get accustomed to the stressful situation and with their own responsibilities that are often overlooked, left without proper practice. Except for training purposes, we also made a draft of informational sources that would be needed in attempt to create simulation of the city. Initially thought of as a warning tool for the case of crisis phenomena, later we realized the potential of creating so-called virtual twin of the city. It will give us a better idea about the city and its traffic situation. That is also one of the reasons we studied possibilities of simulation in context of resilience, and how can the simulation help us with its indicators. Information transferred to the program should include meteorological information, flood risk information, information about dangerous substances leakage and air pollution, GPS tracking of IRS units, and information from video surveillance and other traffic measuring sensors that deliver transport data needed for visualization of transport resilience, as mentioned in the previous picture. Potential contribution can be seen in warning signals from linked sensors, mentioned scenarios and trainings for executives, in visualization of possible failure consequences, and in estimation of development of crisis phenomena that we can achieve by putting crisis phenomena into the simulation of normal day, which means after we will connect all sensors, and most importantly, after we will be able to simulate movement of vehicles and pedestrians around the city during the days of the week. In the city of Žilina, we were partially successful with collecting the data from the city center. We have already besieged the center with the sensors, collecting the traffic data, and we hope to link those data with the simulation program. Start from there, then add another sensors, such as those from meteorological station of our university. And hopefully we will be successful in connecting all necessary sensors to visualize the city, to visualize its resilience, and to achieve higher levels of resilience and safety in the city. And that concludes our presentation. Thank you for your attention. If you have any questions, do not hesitate to contact me or my colleagues.